Alright, so I thought I'd consider Aristotle's wheel paradox, because a lot of the things I've been talking about lately actually come to play here. Okay, so the question at hand with the wheel paradox is how it comes to be that circles of differing diameter, attached to the same axle and rotating at the same rate, the same RPM, can roll along parallel lines of the same length, right? So we're looking at the like the bottom of the wheel, like where it touches, right? That path, right? So we're not mapping a point on the wheel. We're looking at like the straight line that the bottom of the wheel draws. Okay. If the larger circle represents a tire in contact with the ground, and the smaller represents the hub, and then as the whole wheel rotates, the hub and tire make one revolution in the same amount of time, and the whole assembly has traveled one distance. That is, every part of the wheel moved the distance of the tire's circumference, despite the tire being the only circle on the assembly with that circumference. So, how can it be that the hub, whose circumference is smaller than the tires, draws out a path that is not the length of its own circumference, but the larger length of the tire's circumference? Right? This is the paradox. This paradox is notable not because it's interesting unto itself, right? I mean, obviously everything's attached, so as you move it, however you rotate it through space, it's all going to move together. Okay, so as far as the paradox itself goes, it's not that interesting. Okay, but because it is a problem of dividing infinities, and yet the vast majority of proposed solutions never take the Archimedean property into account, it is somewhat interesting. Right? It's interesting because of the historical nonsense that's gone into trying to explain this. If our two circles have a linear scaling between them of k to 1, okay, I need to not be scrolling, there we go, where k is some value between 0 and 1, exclusive, then the smaller circle must draw a line, and it's exclusive because if it's 1, then it's just the outer, so that doesn't do anything, and if it's 0, then something else happens. The smaller circle must draw a line of length 1 on k times its circumference. Thus, if we make regularly spaced markings on the circumference of the smaller circle, the gaps between where they land on the drawn line will be 1 on k times their spacing on the circle itself. So, does the smaller circle slip? Okay. This is kind of the crux of the paradox, asking whether there's slippage on that little wheel. Okay. When analyzed in terms of a limit, where the circles are replaced with regular polygons, the answer appears to be that it does. However, it's worth noting that when the circles are modeled as polygons, the gaps which appear in the line drawn by the smaller polygon result from the rotation of the assembly forcing the hub upward and out of contact with the line whenever the tire is contacting the ground only at a vertex. So this approach does not genuinely inform us of anything about the behavior of the circles we're attempting to model. Okay? So because the distance from the center of the polygon to a vertex is greater than the distance from the center of the polygon to the center of one of the sides, you get, as the polygon rotates, you get it pushing up off of the surface. Like, so the center of the wheel, if it's a polygonal wheel, actually will bounce up and down. Okay, and this affects the entire wheel assembly. So the hub also does this. It hops. It's not slipping, it's hopping. Right? Further, if we attempt to model the problem with a physically real circular wheel, entirely different difficulties arise. Namely, the tire does not contact the ground at a single point, as in the mathematically idealized problem. Instead, it has a contact patch, which is a roughly rectangular shape, depending on the tire. The point we're attempting to model as the contact point lies somewhere within that contact patch, and as the wheel rolls, this patch reacts in some fairly complicated ways. Indeed, the entire notion of slipping comes from observing some of these effects, as our idealized contact point may not fall in the center of the physically real contact patch, right? Because there's going to be some distortion, even if you're using like steel, right? there's going to be some degree of distortion and things happening there. So we are forced to analyze the problem on its own terms. When we consider perfect circles moving along a perfectly straight path, with absolutely no slipping between the tire and the straight path, and an idealized point of contact between the tire and the path, we get something quite different from what our models suggest. Now, because the hub is a perfect circle, and there are no effects which move the hub off of its path parallel to the tire's path, and because the circumference of the hub is a continuous line to which the Archimedean property applies, it must be the case that whenever the tire's contact point changes, so too does the hub's. That is, despite a length w on the hub's circumference correlating to a length of w on k along the hub's path, no point on the hub's circumference ever slips along the path. Since this arithmetic manipulation of a continuous length cooperates with the Archimedean property, such that a distinct point on the hub's circumference is always moved into contact with the path, regardless of how small the rotation of the wheel. Thus, there is a bijection between the circumference of the hub and the circumference of the tire, despite them being in a ratio of k to 1. Right? So, there is, another way of putting this, there is exactly as many points around the smaller hub, the smaller circumference, as the larger circumference. There's exactly as many points. There's a bijection between them. Okay? It should be pointed out, however, that there is a case where this does not apply. This is when we consider the center point of the circle. This is why our range 0 to 1 was exclusive. Right? 0 behaves differently. This point, being a point, cannot rotate per se. So it does slip the entire distance. It's just dragged along that line. It's just pulled through that line. Thus the entire wheel, save the center point, behaves the same way. So we can say that 1 minus L naught of the wheel exhibits no slipping, because precisely 1 minus L naught of the wheel is subject to the Archimedean property. You might notice, if we take the Archimedean property as an axiom, you can never arrive at this realization. And thus, Aristotle's wheel paradox remains paradoxical. It remains unsolvable. But when we recognize that the Archimedean property does not actually apply everywhere, and thus cannot be a valid axiom, things get a little bit simpler.